Hi everyone, welcome back to yet another Euphoria Academia YouTube video. Today we're going to be doing the grade 12 Physical Sciences paper 1 that was done in November 2024. We're going to be covering electronic circuits in this video. My name is Ole and I'll be taking you through it, so strap in and let's get a move on. As stated before, we're going to be doing electric circuits rather in this video, and we're going to be doing question 8 in the past paper. As you can see, this question starts from 8.1 and ends at 8.3, and it was worth 21 marks. With electric circuits, and I guess with physics as a whole, a person really needs to pay attention to every information that is given, right? So question 8 starts and says L1 and L2 are two light bulbs that have the following ratings. L1 has a power rating of 36 watts and a potential difference rating of 20 volts, and L2 has a power rating of 48 watts, and a potential difference of 32 volts. So the two bulbs are connected as shown in the circuit diagram below. The battery has an internal resistance of 0.6 ohms, while the conducting wires and the ammeters have negligible resistance. R1 and R2 are resistors. Okay, cool. So let's just try and explain what is going on, because that'll be very key. All right, so this is our battery, and we were not given an EMF, but we were given an internal resistance. So we already can expect a question where it asks us to find the EMF of this battery. All right, and we have a resistance R2. We're given a resistance 4 ohms, which was not mentioned in the information above. All right, and we have a parallel circuit. So in a parallel circuit, we know that the voltage across these two paths here will remain constant, but the current will split. The current will split depending on how much resistance each path presents. We might have a higher current going into one than the other one. All right, so I'm just gonna write that. Forgive my drawing. All right, so we might just have an I1 and an I2, and the current will go through the light bulb, through the resistor, and then it will join up until A1. A1 is the ammeter, and that will read the total current. So it will read I1 plus I2. All right, and we already know that the voltage will be the same. So the voltage across a parallel circuit is constant. All right, cool. But it's important to note that across each resistor or across each load, there will be a voltage drop. So the voltage will drop here, and it will drop here, as well as it will drop here. But when you add all these voltages, so your V2, your V1, your VR1, that should be equal to the same thing. That should be equal to the parallel voltage across these two paths, right? So that was just a lot, but I promise it helps, because now we understand exactly what's going on in the circuit. So without further ado, let us get through the questions. Question 8.1 asks us to define the term power. Now, in physics, there will always be definitions, so you need to learn these definitions. But for this answer, power is the rate at which work is dissipated. And that should be your 2 marks. 35 seconds. Let's go. Okay, question 8.2.1 is asking for the reading on ammeter A2. Right now, an ammeter reads the current, right? So we're meant to find the current. And in the question before we even started, is stated that we need to work with the light bulbs with their ratings. So that means they have to work as stated in their ratings. So their ratings state that L1 will have a dissipated power of 36 watts and then a voltage of 20, and then L2 its own value. So what this means is that these light bulbs cannot operate above or below these ratings, otherwise they will not work. So in this circuit they work, so we now know the power dissipated as well as the potential difference across these light bulbs. All right, without further ado, let us find what the current is at A2. Now, the current will be the power equal to the velocity multiplied by the current. That's the equation that I'm going to use to find the current because we already have the power. The power for L2 is given as 48 watts, and then the voltage is given as 32 volts, and we're trying to find the current. We just do our algebra and we will find that our current is equal to 1.5 amps. For question 8.2.2, we're asked to find the reading on A1. So that the current, they were meant to find the current, which is, as stated before, is the total current. So what we can do is just find what current is flowing through the second branch, and we will call that current I1, just to make things simple. All right. So as stated before, we're still going to use the power equation because we know what our rated power for L1 is, and it was given to us as 36 watts, and then the voltage across it was given to us as 20 volts, and we're trying to find I1. And when we do our algebra, we will find that our I1 is equal to 36 divided by 20, which is going to give us a value of 1.8 amps. Now, the total current, as stated before, is a combination of I1 plus I2. We already found I2. Our I1 is 1.8 amps, and our I2, we found that to be 1.5 amps, and in total that will give us a total current of, my mistake, 3.3 amps. For question 8.2.3, we're asked to find the resistance on R1, so we need to find what value R1 possesses. All right, so we know the current through these branches. I just like stating the things that we do know. So we know the total current, we know I1, we know I2. All right, and we actually know, what else do we know? We know the voltage across L2, we know the voltage across L1, and yeah, and we know what the parallel voltage ought to be. All right, so we can actually use the voltage as well as the current to find what our R1 resistance is going to be with regard to the voltage drop across it. All right, so let us get into it. So we're trying to find what our VR1 is, what our voltage across VR1 is, and we know that it plus the voltage across L1 will be equal to the parallel voltage. All right, this just means that we will have the same voltage across these two branches. You'll see when we do our mathematics that things are going to work out. So we don't know our VR1. Our VL1 is the rated voltage across our L1 light bulb, and we were told that that is 20 volts. Now, for our V parallel, we know that we have the LED, the light bulb in this case, L2, that has a rated voltage of 32 volts, and it is the only resistor, the only load in that branch. In that branch, yes. So that means that it will not exceed the total parallel voltage. So it must mean that the parallel voltage across these two branches is equal to 32 volts. All right, now with that, we can even find what our R1 is, and our R1 is going to be equal to 32 volts minus 20 volts, and that is going to give us 12 volts. All right, now we were told to find the resistance. We know the current already, so our R1 is going to be equal to our voltage over our current. Let me just write the subscripts. Our current through R1, in this case our I is just going to be I1. Now our VR1 we just calculated as 12 volts, and our current through through that resistor, we know it as 1.8 amps, and that is going to give us 12 divided by 1.8. That is going to give us a resistance of 6.67 ohms. I just rounded that off to the nearest two decimal places. Question 8.2.4 is asking for us to find the electromotive force of the battery, right? And we know that the electromotive force is equal to, just gonna write down the formula I, and then big R will be the total resistance across the whole circuit, and then small r will be the internal resistance of the battery. Now the formula is the V external, so the total amount of potential difference across the whole circuit, and that will be added to our total current multiplied to our internal resistance. Now, in all these cases, we actually need to know the resistance across our whole circuit. I'm just going to use this formula, but you can try and use it, the second formula, if that will help you. All right. Okay, so we need the total resistance across this whole circuit. And the total resistance across this whole circuit will be made up of this resistor, which is R2, which is in series to the battery, and then the resistance across these two branches, or the parallel circuit that we have. All right, so that will be equal to R2 plus the resistance in the parallel circuit. Now we already have R2, so we just need to find our resistance in the parallel circuit. Now our RP formula will be something like 1 over RP, will be equal to, in this case, the 1 over RL2 plus the 1 over RLI or L1, sorry, plus our R1 resistance. Now, in our formulation, did we actually find how much resistance our L2 has? I do not think so. So we can quickly calculate it, and we will find that it will be the voltage over the current, and that will give us a voltage of our L2. Our voltage was 32 volts over our current, in this case, was 1.5 amps, and that is going to give us a total of 21.33 ohms. All right, now our resistance across our L1, that we actually didn't find it as well, so that will also be voltage, and then our current across L1, and that is going to give us our 20 volts over our 1.8 amps, and that will give us a number of 11.11 ohms, and then we already have our R1. So let us just substitute into our formula, and we will find that that will be 1 over 21.33 ohms plus our 1 over 11.11 plus, now what did we find our resistance to be? That was 6.67 ohms, and that will give us, we just have to put that all into a calculator. That will give us plus 1 over 11.11 plus 6.67. That will give us a value of, well, in the calculator it just types it out as 0.1032 ohms. That is equal to our 1 over Rp. Now we have to apply the inverse, meaning that our Rp is going to be equal to, so our answer, we're just gonna apply -1 to, we're gonna raise it to the power of -1, and we're going to find that we have an answer of 9.697 ohms. And what we can do then is we'll know that our EMF will be equal to our total current. We found that that was 3.3, and that will be multiplied to our Rp plus our resistor across the in series, sorry, so that will be 4 ohms plus 9.697 ohms, and that will be also added to our internal resistance of 0.6 ohms, and we will find that our EMF of the battery is going to be equal to 3.3 multiplied to 4 plus 9.697 plus 0.6. That is going to give us an EMF of 47.18 volts. Alright, for the last question, 8.3, we're given a whole story there. We're told that bulb L1 burns out after a while, and then we have to assume that the resistance of bulb L2 will remain constant. Will L2 remain burning even after L1 has burned out. So essentially what has happened is now we don't have a parallel circuit. This guy has burned out, so now our circuit is just a series circuit flowing from the battery through this resistor, through L1, and then back to our battery again. All right, so question is, if the resistance across L2 remains the same, will it still burn essentially? Will it still glow? Will it still light up? That's the question. All right, so let us find how much current is actually flowing through L2, all things considered. So we already know that our EMF is equal to our I, and then that will be the equation. So we know that our EMF is, let me just go back to it. Our EMF is 47.18, not this 15 that we are seeing right there. That is an error. 47.18 volts, and that will be equal to, we don't know our current yet. We know that our resistance is the same, so we have our 4 ohms, which is R2, plus the resistance across our L2, which we found as 21.33 ohms, and then we have on our internal resistance of 0.6 ohms. And after doing some maths, we're going to find that our current now flowing through the circuit, the current will not split, it will flow through all the components, will be the same, and that is we're going to find as 1.82 amps. Now, if we compare it to what we had before, our I2 was actually 1. Our I2 was 1.5 amps. So this new I is actually quite, well, it's higher than our I2. So that means the current that is flowing through it, even though the resistance is the same, is quite higher, and that's quite dangerous. All right, and essentially from this you can already see that the bulb will not glow. So the answer is no, but let me further explain it by writing another equation. So we were told that the light bulbs need to work in their ratings, right? They can't, that means that they can't exceed them. That means they can't go over them. They can't go below. They can't go above. They need to be those ratings. So we know that the power for our L2 bulb is going to be 48 watts. So what's this new power? And this power is essentially the the energy or the work that is dissipated, right? So it can only take 48 watts. You know, that's the max. It can't go over, and sometimes it can work below, but let's just say that's the number that we need to be looking at. What's the new power that we have? Right, so the voltage is still the same at 32 volts, and that is multiplied to the current that we just found, which is 1.82 amps, and that new current that we just the new power then will be 32 multiplied by 1.82 amps, and that will give us a new power rating of 58.24 watts, which is also quite high compared to that. So at some point this bulb will blow, and it's basically operating above its limitations. So no, bulb L2 will not glow, it will not shine, and that is it.